Dear Grade 8, welcome to this first video lesson on work, energy and power. We are going to have a series of lessons on this particular section. This is a vitally important section in physics. We start early with you in Grade 8, which is normally earlier than normal. Generally speaking, work and energy and power is done either in Grade 9 or in Grade 10. And then again in Grade 12, where it is a very important and often very challenging section of the matric syllabus, and certainly the questions that occur in the final exams are often very challenging. So in this first video lesson, I'm going to focus on the concept of work. Now, when we talk about work in physics, we are not talking about work in the same way as people generally refer to work. Let me give you an example. So let's say, for instance, someone goes to work and does a job. Well, we know that they put effort in to go to their job, and then they spend a lot of time and a lot of energy doing whatever they do. And when they come home, they say they've done work. Now, that's not the type of work we are talking about. Another example would be, for instance, if I had to go to the gym and I had to work out. Well, we would be doing work, as we'll see later on, according to the definition and concept of work in physics. But when we talk about working out, we're not referring only to that. We're referring to the fact that we're putting a lot of effort in. So when people talk about work in physics, we're talking about energy transfer. But when people talk about work in everyday life, they're actually talking about effort. And effort in physics is actually a force and not energy. So the term work in physics is an unusual definition. It's an unusual concept, but it's a very, very important concept. So here is one of the definitions. This is the definition we are going to use in the Grade 8 syllabus, and that is that work is done when there is a transfer of energy through a force which moves an object over a distance. Now, this is really very important, and I'm going to try and explain it by using an example. So let's say here's Mr. D, and Mr. D is standing there, and I am pushing against a chair. Let's say this is quite a heavy chair. So it's a nice big thick wooden chair, and I'm applying a force, and here is the ground. Now, this is a very heavy chair, and I apply a force. So this is going to be the force of Mr. D on the chair. So we are using a convention here that we use frequently in physics, and that is of specifying a force as follows. Force of the agent, or the source of the force. The agent is the source of the force on the object. So Mr. D is the agent. Mr. D is the agent, and the object is the chair. Now, I push on this chair, and let's say I apply a force of 10 newtons. So I'm not pushing very hard, and the chair doesn't move. Now, the question is am I transferring energy to the chair? Well, the answer is yes. If I do this for long enough, I'm going to feel me being drained by my effort. However, according to this definition, work is not being done, because albeit there's a transfer of energy through the force of Mr. D on the chair, it's not enough to actually move the object. And so this is often what confuses learners, is that they don't understand that work is only done when there is a result in the form of motion. And that isn't our experience. Our experience is we can go and we can push against a wall, and after 2 minutes we're sweating, but the wall hasn't moved. So in actual fact, according to this definition, we haven't done work. So now, if Mr. D now wants to move this chair, he might need to apply as much as 100 newtons. So now, if this 100 newtons is greater than the friction between the chair and the surface, and we're not going to go into too much detail about that on grade 8 level, well then this chair is going to move. And when it moves, apologies for that, when it moves, then work is done. So as soon as this chair moves over a distance d, and let's say this distance now is, let's say, 8 meters, so that the chair now comes to a standstill there, then what we find is that the chair moved because it gained energy, but it gained enough energy to move it. And so therefore, effective energy was transferred. So now we need to be able to work out quantitatively how much work was done, how much energy was transferred. So in physics, we love to describe things in mathematical terms. So we can say W is for work. Now one has to be careful because remember we've also worked with W for weight. So we are going to work with big W for work and little w for weight. So little w will be mass times gravity, and big W will be the change in the energy of the object. And this is in actual fact the work done by the agent. Right, so the formula that we're going to use is such a smart formula because what it does is it actually includes the following prerequisites or conditions that need to be met in order for work to be done. So the three prerequisites, a prerequisite is something that needs to be happening in order for something else to happen. Right, so firstly there must be a force exerted on the object. The object should move as a result of the force, and the object has to move in the direction of the force. Now, in grade 8, we're going to have that as a condition. However, when we get to later on in grade 11 and in particular grade 12, friction, for instance, will do work, even though it's acting in the opposite direction to the motion, but then it does negative work, which we are not going to work with in grade 8. Negative work means that the agent is actually removing energy from the object. Like, for instance, the brakes of a car or a bicycle that remove energy from the car or bicycle to slow it down. But we're not going to work with that. So the formula is that work equals force applied times distance. Work equals force times distance. And in our syllabus in grade 8, we're going to work with the force being parallel. In other words, in the same direction as distance. But in grade 12, you will work with, for instance, a force that may not be parallel to the distance and will have an angle between the force and the distance. But then one needs to use a more sophisticated formula for the work done, which is beyond the scope of this course because you need trigonometry, which you haven't done yet. So using a formula triangle, we can now represent this formula as follows. The work done is equal to the force times the distance, or the force is the work divided by the distance, or the distance is the work divided by the force. So now it's important that we work with newtons for force, distance in meters, so that's really important. It's important that whatever distances we work with, they need to be in meters. So we're going to have to convert them to meters if, for instance, they're in centimeters or millimeters or kilometers. When we dealt with weight earlier in the year, we learnt about newtons, but joules is something new to us. So we need to define the joule. So the unit for work is the joule, right? And the joule is defined as follows. It's 1 joule of work is done when a force of 1 Newton moves an object through a distance of 1 meter. Right, so looking here, we can say, well, that then means that 1 joule is 1 Newton meter. That 1 joule is 1 Newton meter. Why? Because if work is force times distance, and we are looking at 1 joule, then 1 Newton times 1 meter gives us 1 joule, but 1 times 1 is 1, and newtons times meter. So this is what we would call unit analysis, where the joule is in actual fact a Newton meter. And so it's nicely illustrated here. 1 Newton moves an object in the direction of where it's moved, in the direction of the force over a distance of 1 meter, that is 1 joule. Now 1 joule is actually quite a small amount of work and energy. So invariably we land up working in practice in kilojoules or in megajoules. So for instance, when we start talking about calories in food, calorie is a unit of chemical potential energy, then often when you transfer it into joules, you're working with kilojoules, not with joules. So now let's move on to some tricky situations which we need to know about before we start doing more calculations. So let's consider some tricky situations. I've already spoken about this kind of situation. So when you push against a tree or a wall and the tree does not move, no work is done because there is no motion. Okay. Now that does not mean that there isn't effort, because the force that this lady is applying to the tree, this force is also called the effort. So we definitely feel effort because we're applying the force, we're pushing on the tree, and according to Newton's third law, for every action there's an equal and opposite reaction. The tree is actually going to apply a force that is equal in size but opposite in direction. So this would be the force of the tree on the lady. So we're going to feel the tree acting on us, but there is actually no work being done. Certainly not on a macroscopic level. In actual fact, on a microscopic level, the muscle fibers in this lady's arms and legs are actually expanding and contracting and are moving, and in that work is being done. And so in actual fact, on a microscopic level, energy is being transferred and work is being done because the muscle fibers are actually moving. So there's force causing movement, but we don't see it because it's on a microscopic level. And that's why we get tired. That's why we expend energy. Anyone who does a bit of gym or anyone who does sport will know that if you now do, for instance, planks, where you're not really moving, but you're trying to remain stationary, very, very, very quickly you get tired. The same as if you go and you now squat with your back against a wall, and you now try to sit in that position with your top of your legs parallel to the ground, that after about a minute, you start to get tired. It's because of that expansion and contraction of your muscle fibers. But macroscopically, on grade 8 level, we're going to say no work is done because we don't see the wall moving, we don't see the person moving, we don't see the tree moving, we don't see the person moving. Now, next one. We have a Pakistani bowler bowling here, or throwing a ball, and the important thing here is that once a bowler, okay, in this case seems to be a bowler, has released the cricket ball, no work is done over the distance the ball travels before being hit by the batsman because no force was applied. So if you are asked, so what work is being done by the bowler's arm on the ball once the ball leaves the bowler? Well, the answer is no work is being done by the bowler because the bowler is not in contact with the ball, so he's not applying a force on the ball. However, there's another force acting on the ball that's doing work on that ball, and that is gravity, because the force of gravity pulls the ball toward the earth. So the earth is doing work on the ball. Also, friction is slowing the ball down, so friction is doing work on the ball. So we need to actually be specific about which agent we are speaking about when it comes to what work is being done. Now, this one is particularly tricky. So if you walk with your school bag in your hand, scientifically no work is being done. Now notice the wording here. No work is being done by your hand. It doesn't say no work is being done on the bag because the bag is moving, but no work is being done by your hand. And that's because the applied force that is holding the bag against falling due to gravity is perpendicular to the direction of motion. So if we had to draw a free body diagram here, there is the force applied, and here is the distance, the direction of motion. The distance is in the direction of motion, and these are at 90 degrees to each other, so no work is being done here because in the direction of the force, there's no movement. However, as soon as you lift that bag and there's movement in the direction of the applied force, then work will be done by your hand. So what is doing work to move the bag? Well, when you walk, you actually push against the floor, and the floor applies a force, according to Newton's third law, pushing you forward. That's why if you're on slippery ice and you try on an ice rink and on a skating rink and you try to walk, you slip very, very quickly because you're pushing back, but because you're sliding, you're not giving the ground opportunity to push back on you, so you actually fall on your face. So now, the force of the ground on your feet pushes your body, so it's doing work on your body, pushing you forward, but now the briefcase or the school bag is attached to you and is part of your body system, and therefore when the floor does work on you, it's also doing work in moving the bag forward. So, but we're not going to go into this level of detail in grade 8. So let's now look at the first example. We have a box that is pushed with a force of 25 newtons over a distance of 2 meters on the surface of a table. How much work is done on the brick? Now, the first thing we need to do is to check that the force is in the direction of the motion, which it is. Then we can say, well, work is force times distance. And so step 1 is the formula step. Step 2, as I've taught you, is the substitution step. So 25 newtons times 2 meters means that the work done is 50 joules. So what that's saying is that whatever the agent is that's applying the 25 newtons, it's going to lose 50 joules by transferring those 50 joules through the force to the box to move that box. We're going to learn later on that in this case what the agent is doing, whether it's Mr. D pushing a box or whether it's someone else pushing the box, that they are changing the energy of the object, which was originally stationary, into kinetic energy. So there's a transfer of energy, work done by the agent is transferring energy to the box, and in doing that, there's sometimes a transfer in the form of energy. But we'll learn more about that later on. Now, if we look at the second example, if a bag of cement is lifted by a 400 Newton force when 2,000 joules of work is done by the hoist lifting the bag. Determine the height that the bag has been lifted to. So what we have here is we have a bag of cement. There's the bag of cement. And it is being lifted by a force of 400 newtons. But we don't know the distance over which it is lifted. So that distance is going to be the height that it is lifted to. We don't know that. That distance is unknown. But we are told that the force transfers 2,000 joules of energy by doing work on the bag of cement. Now, if anyone's ever lifted a bag of cement, you will know that to try and lift a bag of cement, a full bag of cement, takes a huge amount of energy. By the time you're done lifting it, you really are tired. So the question here is what is the height or distance? So using the formula triangle, we know that work is force times distance, where the vertical line is times, multiply, and the horizontal lines are division. The unit for work is joules, the unit for distance must be meters, and the unit for force must be newtons. Now, we want to work out the distance. So we have the weight, we have the force, we're looking for the distance. So the distance is the work divided by the force. Here we go. The distance is work divided by force. The substitution, the work is 2,000 joules, divided by the force is 400 newtons, the distance is 5 meters. So it's imperative that you use the 3-step method. Step 1, write down the correct formula in the correct form. Step 2, substitute the values in with the correct units. And step 3 is that we work out the answer and ensure that the correct unit is there. Let's now consider a third example. The work done to move an object horizontally 0.8 kilometers is 2.5 megajoules. Calculate the force applied to the object. Now, what I would like you to do is to pause the video and attempt this problem on your own using what I've just taught you. And once you've done that, you can start the video again and then you can see how I solve it. So, now that you've attempted it, let's set up a data list. So, even though a data list is not explicitly required and there are no marks allocated for it, it's a good thing to set up a data list because what it does is it enables you to see what you've been given and what you need to solve for. It also explicitly shows you whether you need to convert your units by using prefixes or conversion factors. So, in this particular problem, we are told that the distance is 0.8 kilometers. Now, immediately, we should convert this to meters because we know that when we work with work is force times distance, the distance should be in meters. So we're going to multiply by 1,000, and that's going to give us 800 meters. We're told that the work done is 2.5 megajoules. Now, recall that prefixes are very important. So, kilo means we need to multiply by 10 to the 3. Mega means we need to multiply by 10 to the 6. So 10 to the 3 is multiplying by 1,000. 10 to the 6 is multiplying by 1,000,000. And giga is multiplying by 10 to the 9, which is 1 billion. So this is 2.5 megajoules. So we are going to multiply by 10 to the 6. So this is going to be 2,5 times 10 to the 6 joules, or 2.5 million joules. What we are needing to determine is what is the force applied. So that is unknown. So I'll write down here that we do not know the value of the force, so therefore that's what we are going to solve for. So going to the formula triangle, we write down W is force times distance, and we should know that the vertical line represents multiply, the horizontal line's division. So if we're looking for the force, then step number one is that we need to write down the formula. So the force is work divided by the distance. So that's the formula. Step number two is the substitution step. So we substitute in that the work done is 2.5 times 10 to the 6 joules. And the distance we worked out was 800 meters. So this is 800 meters. And so step number three is the final answer, which we're going to work out. We take our calculator, say 2,5 times 10 to the 6 divided by 800, and that's going to give us an answer of 3,125. Now, what unit? Well, work needs to be in joules, distance in meters, and force in newtons. So the answer here must be in newtons. And so therefore, a force of 3,125 newtons needs to be applied by the agent on the object over a distance of 800 meters to do 2.5 megajoules of work. So I hope that this short video lesson has helped you to understand the concept of work done on a level that is satisfactory for grade 8, and that will be a good base for what we're going to do in the next few video lessons on energy, kinetic potential energy, and on power. So thank you for viewing this video lesson.